Here's a second problem that's also very common. You have a beam, I've drawn here, with a point load P right in the middle of the beam. The total length is L, so L over 2 on each side. I'm going to get the reactions. It's symmetric, so that reaction is P over 2. That reaction is P over 2. I'm next going to take my slice, close the loop, and draw the free body diagram. We've got this piece of the beam. We have this reaction, P over 2, and that load P is not in our loop as we've drawn it. And so here's X. Before we continue, let's talk about the fact that P, that load P, is not in our picture. It's not in our free body diagram because it's outside of the loop. However, if X is greater than L over 2, then the cut, let me draw it in purple, would be out here. And then when we close it, P would indeed be in the loop. So let me draw the purple free body diagram. We've got something like this. We have, in the purple, we still have this P over 2, but now we have this P in here. This distance here is L over 2 to the P, and the distance to the cut is this X. What this means is that we'll have two different answers depending if we are to the left of P, or X is less than L over 2, or if we're to the right of P, that is, X is greater than L over 2. This means we'll have two sets of equations. We'll have one set of equations for shear and moment for the red. Let me draw that in. Remember, on the right side, shear is positive going down and moment is smiley. We'll get one set of equations for the red. And let me draw in the shear on the purple one. Again, on the right side, V, or shear, is positive going down on the right, and moment is smiley. There will be a different set of equations for the red, V and M, than the equations for the purple, V and M. We'll have two sets of equations. Let's solve these two in parallel. We'll have sum Fy equals 0. We have P over 2 going up minus V coming down equals 0, or V equals P over 2. On the purple side, we'll have P over 2 going up minus P going down. I'm looking at the purple free body diagram. Minus V equals 0. And solving for V, we get V equals minus P over 2. It's interesting. You have positive P over 2 for shear in the red, and you have negative P over 2 for the shear in the purple. And it transitions at L over 2, right where that point load is. Next, let's take some moment about the cut is 0, counterclockwise as positive. You have that P over 2 times the distance X. Let's see, that's positive going clockwise around, no, it's negative going clockwise around the cut, plus M, that's it, equals 0. Or you have M equals P over 2 times X. Doing the identical thing for the purple free body diagram, we have that reaction of P over 2 times that distance X, and that's going clockwise around the cut, so again negative. It's the same as before. But now we have this P. It's plus P times the distance from P to the cut, which will be X minus L over 2, right? That's that little leftover distance. It's X to the cut, and P is L over 2 from the left end, so the distance from the cut is X minus L over 2, and that's going counterclockwise around the cut, so positive, and we have M equals plus m equals 0. Solving for m, we get m equals p over 2 times x minus p times x minus L over 2. Expanding that out, p over 2x minus p times x plus pl over 2. And that comes out to pl over 2 minus p over 2x. Let's plot the purple and red equations for v and m. Again, we're going to draw these right below the beam. Here's I've pasted in a picture of the beam and v and m. What I'm going to do is I'm going to copy the equations, bring them down here, and I'll show you what the plots look like. Here are the equations for the shear for the red side to the left of P and the purple side to the right of P. It's just V is P over 2 if you're to the left of P. So let me just draw in that plot. It's just a constant at P over 2. And if you are on the other side, it's negative P over 2. So let me draw that in here, minus P over 2. Now, traditionally, we finish off these plots by drawing, we box in the end there for the purple, we box in the end there for the red, and we draw a vertical line here to finish that off. An interesting thing to note is that this distance here is a total of P, which is equal to the load, and that's not a coincidence. The jump in the shear diagram from the red down to the purple will always be that concentrated load P. Let's now do the same thing for the moment. I'll copy those equations and paste them down here, and then we'll draw them. I think I forgot to make the V equations pop in like magic. They might already have been there. I never know until I play back the notes. Anyway, here are the moment equations for the left and the right side. Remember, the red is to the left of P and the purple was to the right of P. I'm going to go ahead and plot these. This equation m equals P over 2 times x starts off at 0 when x is 0, and when x is L over 2, it'll equal PL over 4. So let me write that over here, PL over 4. And it's linear, so that equation looks like this. Let's plot the purple equation now. When x is 0, m is PL over 2, which is up here. And when x equals L, we'll have PL over 2 minus PL over 2. It'll be 0 out here. Now, the purple equation is only valid to the right of the point load. So this part of the equation, I'm going to just draw in dotted because it's not valid out here. But to the right side, it is valid. And let me just draw in that line. It looks like that. And when x is L over 2, we get PL over 2 minus PL over 4, which is PL over 4. It matches right here, which it should. One of the key points to this example of shear and moment diagrams is that you have two sets of equations. You have one set to the left of the point load, and you have another set to the right of the point load, because depending on where you took the cut, it changed your free body diagram and therefore changed your equations. You'll learn more about this when you take 3200 in the civil engineering department, or certainly when you take ES 2410 next semester. Whenever you have a beam and you have a bunch of point loads on it, what that will mean is when you take this cut, and then when you take this cut, and even if you take another cut out here, you'll get different equations because you have different loads in there. What this means is that every time you have a point load, that means you have a new set of equations. Therefore, for this problem, you're going to get one set of equations here, another set of equations here, and a third set of equations there. This will have three pairs of equations, three equations for V and three equations for M.